All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. What I want to talk to you about today are determinants, their relation to the area of parallelograms, and their relation to the orientation of vectors sitting in a plane. Um, Often determinants are just, this scary number that's mysterious, and we don't really know what we're doing with it, and it doesn't need to be that way. Let me briefly remind you what a determinant is. It's something that you do with a matrix, and I'll kind of take this out of order. Say we have a matrix. The top row is A1, A2. The bottom row is B1, B2. Then the determinant of that is this number A1, B2 that we get by multiplying this across the main diagonal minus A2 times B1 we get by multiplying the elements of the secondary diagonal. One context where we can get these two rows of the matrix is coming from a vector. We'll often put in a vector A1, A2 as the first row and a vector B1, B2 as the second row. And this can happen in a variety of situations. Okay. Now, one thing important to notice is that if we put these in a different order, we get a different number. Okay. And here, in fact, that if we switch the first row and the second row in the matrix that we're taking the determinant of, that it switches the sign. Okay, that the determinant when we make the A row the B row and the B row the A row is the negative of the determinant the other way. This is why we say a determinant is alternating. Okay, and so the switch of sign is kind of a big deal. Okay, so here I'm going to calculate the area of a parallelogram. First, notice if we have a parallelogram with a base that has length b and an altitude of length h, then the area of that parallelogram is b times h. Okay, now take this out of that's the area in the abstract. If we come to a specific situation where we have two vectors and we have them generate a parallelogram, right? We've got a vector A over here as one side and a vector B over here as the other side, and this vector through the middle is A plus B. Then this is the parallelogram that's generated by A and B. And so let's let the length of the vector A be equal to A and the length of the vector B be equal to B. We can calculate the area like this. Okay, the vector A makes an angle of alpha with the positive x-axis. The angle B makes an angle beta with a positive x-axis. That means that this angle between B and A is B minus A. Okay, that gives us the length of the altitude as being B times the sine of beta minus alpha, and the length of the base as being A. So the area of this parallelogram that's generated by the vectors A and B has this pretty little formula: B times A times B times sine of beta minus alpha. Okay, so let's take that and let's put it in our pocket and remember it. Okay, so now we're having kind of a mathematical crossover here where determinant, I can't even spell, determinant meets area. Okay, and how we're going to do this, we're going to take our vector A and vector B that we had in the previous clip and resolve them into their components. Okay, vector A is equal to A cosine alpha times I, A sine alpha times J. Vector B is B cosine beta times I, and B sine beta times J. All right, and we take these and we put them in a determinant. Then we will calculate that determinant's value. This will be A, B sine beta cosine alpha minus A, B cosine beta sine alpha. And I'm putting this down in an order that might not seem natural to you, but I'm saving a little time on this because I can then factor out the A, B, and this leaves me sine beta cosine alpha minus cosine beta sine alpha, which if you are up on your trigonometry formulas, this is sine beta minus alpha. And so this is the area of that parallelogram. This is exactly what we computed before. So this crossover is pretty good. Now, let's take it because it's more than just area. Okay. And let me draw a little picture. I'm taking a serious risk here, drawing a picture. Okay, so we've got our vector A and our vector B. Now, we have our positive x-axis here. Remember, okay, how we calculate angle. Okay, so the angle from positive x-axis to A comes like this. Positive x-axis to B comes like this. We're going in a counterclockwise way. Okay, and we're brought up all of our lives to think that clockwise is the positive way, and you know we would do it that way if we could, but the thing is the mathematics here just works out so much more sweetly if we take our counterclockwise to be positive. Okay. So we say the angle A sweeps out a positive angle going up clockwise to B, and that positive angle is beta minus alpha. Okay, and so when we put our vectors into our matrix, we put this A vector, the one which comes first away from the x positive axis, we put it in the top line, and our vector B, which comes second as we sweep up from the positive x-axis into the second. And so if we do it that way, it gives us the pure area. Okay, but if we are some reason we get our vector B, okay, coming first, it gives on the top line, if we switch these, it would give us a negative area. Which we don't like negative area, so we invent a new term and called it oriented area. And so the oriented area takes into account the order that our vectors are in, how we're meeting our vectors in the way up from the positive x-axis. Okay, and though it's harder to explain, this works as well at higher dimensions. When we get 3 vectors in, we get oriented volume. Okay, and when you go up to higher dimensions, okay, it kind of beggars our imagination what a 4th dimensional area is, 4th dimensional volume, what is the word, we have to make up stuff. But the orientation part of it remains, because orientation does come in at higher dimensions and is meaningful, and you only have a positive orientation and a negative orientation. And so determinants are powerful, meaningful things. And knowing that helps things make sense as we go along. Yeah, who is it? No, I'm not doing anything. Come on in.